we were talking about, we have already seen various instructions on what are the steps needed to complete those instructions. If you look into the previous class, where I actually talked about how different instructions are designed and how basically the steps are there. Okay. Now we figured it out that there are some steps which are common and some steps which are not common. So, for example, we know that there are stages like fetch, decode, execute, memory, and then write back. But not necessarily that every type of instruction require all these things. So these are stages, and we looked into it that how different types of instructions, for example, move, it requires fetch, it requires decode. Okay, it doesn't require anything here in execute stage. It doesn't require anything in the memory. It requires the write back. Similarly, if you look into the instruction load, fetch, decode, then execute, then memory, then write back. If you look into the next, which is store, you got fetch, decode, execute, memory. You do not record this one. If you talk about ALU or add, it requires fetch, decode, execute, doesn't require memory, write back. So these are 4 important instructions. Other than these 4 instructions, we have, more instructions which gradually we shall see later stage. But at present, these 4 are sufficient to understand how the architecture should look like. Okay. So with these instructions, if you would like to come up with some abstract view of the implementation, then it will be easier for us. So in the last class, if you remember, I was talking about that one of the busiest or most important circuit inside the processor is a register transfer. It's a transfer circuit basically. So starting from register to register, register to memory, memory to register. Okay, intermediate registers. Okay, we require a lot of transfer of data. Now, let us try to understand that from the abstract view, where are these transfers happening? Okay, so we are particularly focusing on 5-stage RISC processors. So these are 5-stage RISC processors. 5-stage RISC. Okay, so in modern processors, we actually have more than 5 stages, but just to understand the concept, these 5 stages are sufficient. Okay. And here you will see that, and you can see that this is common, fetch is common, decode is common, and the execute stage depends whether you require or not. Similarly, memory stage also depends whether you require or not. Write back is also same. Okay. The other, these are popular or common instructions. We also have other instructions like branch. Okay. Then you can have call. Sorry, there was some disconnection from my side. Am I audible now?
Yes.
Yeah, for sometimes there was some disconnection, network disconnection.
After call, what you wrote?
Call return. This is branch call return. Okay. Hopefully now you can see it better. So branch call return. Now these, these are additional instructions. They also require these stages, these 5 stages, F, D, E, M, W. We will see that which instruction requires which stage. Obviously, this fetch and decode, they are mandatory. So we can put actually asterisks over these 2 stages because they are mandatory stages. Fetch and decode. Without these 2 stages, we cannot actually proceed. Okay. So we need a circuit that actually this portion of the circuit is common. It should be common for all the instructions. Actually, when we talk about branch, call, return, they also require this fetch and decode instructions. So what can be a generic overview of the circuit? That is what we are going to do. And then gradually we will see that how the transfer circuits can be designed. Okay. So let us take a fresh page and then design the circuit. So I shall write here, it's a abstract view rather. Abstract view. Of the CPU. So this is an abstract view where basically we also need to mention that where is the memory. Okay, so that's why memory is also part of this. If you don't agree with me, just let me know, because this is an abstract view. You may differ, but I think once I complete this, you will agree with me that why this is a viable solution. Usually, we do not keep memory inside the processor, but since I am designing the abstract view of the CPU, which requires the instructions to be fetched from the memory, that is the reason I am actually putting it. And this is where it is present, whether it is inside the CPU chip or outside. That is not the point. Point is we want to understand the whole data transfer. Okay, and we want to see that there's a lot of disconnections coming, continuous disconnections. So in the memory part, one way it gives the address, other way you get the instructions. Okay, so this is the address, and this is the instruction. Now, where from you get the address? For the next, because this is instruction memory. That's why I have written it instruction memory. This instruction memory gets the address from. Yeah, there's a lot of disconnectivity coming.
Your video is lagging.
Yes, I know that there is a network problem. Let me fix it up. I don't know, in my apartment, so this Wi-Fi router is not functioning properly. Just hold on, let me fix this issue. Is it better now?
Till
Hello?
now fine, sir, but whole paper is not coming.
Yeah, whole paper is not coming. That is the problem of my camera. Okay, because I am unable to. Now it's slightly tilted, but that is what I can do at best.
Okay.
No, sir, it's not visible. So your camera is focused on your phone.
Now?
Fine. Yes.
Yeah. Okay. So if you look into this, we actually have taken two units. One is a program counter and there is the memory. So this is a memory. This is memory. So it's outside entity. But I told you this is a conceptual or abstract view, so we don't mind it even if bringing the memory inside the processor. Okay. These are logical connections only with respect to the stages that we talked about earlier. Okay. Now, where from we get the value of the program counter? It comes from a circuit. Okay. So the value which is stored in the program counter, which goes to the address port of the memory, also needs to be used for some other purpose. Can someone tell me that why do I need this value again?
Program counter, sir.
Yes, program counter value. This line, if you look into this, this value of program counter goes to the address. So, and it basically fetches the next instruction. I'm talking about, do I need to take this value again for doing something?
For incrementing it.
Right. So I can easily take the value here itself. Okay. And what I will do, so what will be here? On the other, this is an adder. What will be here?
1.
It will be 4. Because you are talking about RISC 32-bit. Next address will
Can
be?
you tilt up a little bit? Add whole page is not moving. Beyond add.
This one.
Yeah, some portion.
That is not visible, sir.
Okay, sir.
So it's 4. Okay. So program counter value is added with 4 and you get a new value of the program counter. That's what I wanted here. So this is basically PC plus 4. The output is PC plus 4.
Yes, sir.
The output is PC plus 4. Okay. Now this value may be used or may not be used. That we will see, but we will preserve this value. PC equals to PC plus 4, we will preserve. Okay. Let's go to the other part of the circuit. On the other part of the circuit, we require to do the operation. Now, the instruction comes here, and The instruction try to fetch or get the values. From where it will get the values? The operands, where do you get the operands? So what if I put a logical block like this, what can be this logical block? Anyone? Any guess?
Register access or something.
Yes. So this is registers. So because there may be multiple registers, so you can keep it like this.
Yes, ma'am. Yes, ma'am.
So why I have given 3 lines? Can someone tell me that why I have given 3 lines? Yeah. Any guess that why 3? Why these 3 lines? 1, 2, 3. Any guess?
Mostly maximum 3 registers have been operands, like in add 2 registers and store in third.
Absolutely right. So you need 3 addresses of the registers. That's why you can have maximum 3 register values. You don't need more than that. Example is add R1, R2, R3. So you need to know the address of R1, address of R2, and address of R3. That is the reason that we are actually giving 3. Absolutely right. Now, see, whatever the value is coming, it is the entire content of the instruction. Okay, so you can assume that instruction register is also here within these register files. All the registers. This is not only general purpose register. This contains all registers. That's why this is an abstract view. This is an abstract view. Okay. The registers inside this file may be separated at later stage. Okay. Now, I also say sometimes I need to change this PC equals to PC plus 4. So obviously one option will be the PC equals to PC plus 4 will be back and it will go to this. But this is not necessarily always true. We may also need to change it. When?
Branching.
Call and jump.
Right. Branching. Call and jump branching. So what kind? Any kind of branching. So where from you get the branch values?
Registers.
From the instruction itself.
Yes, sir.
Branch value is given. So some portion you may get it from the here also.
Sir, but they first need to be decoded, right?
No. Why it need to be decoded? It will automatically come.
First we need to separate that this is the branch instruction and where we should branch.
I know that, but these are adder circuits. Okay. these adder circuits will be activated if needed. If the branch is not needed, then this circuit will not be activated, only this will work.
Okay. I got it. It
That's
will
why
not always add.
it will not always active. They're not always active. I am telling you, this is an abstract view. Okay. All these components need to be active at right time. It will not be active at always. So that's why this kind of arrangement is okay, fine. So sometimes you get PC equals to PC plus 4. Sometimes you get PC equals to PC plus 4 plus the offset. This is basically offset.
Multiplier.
Is that clear now? At least this part. We shall see that how to design this portion. This is an abstract view. That's why, you know, I am skipping a lot of things. But you can understand that we require an arrangement something like this, where a couple of adders will be there. One adder will add 4 with the PC. Another adder will, if needed, will add an offset value with the updated value of the program counter. That's it. Now let us go to the front of the circuit. Now this portion. So we are with the registers now. Now after that, what will be the logical block after the registers? So this is my RF, register 5. Anyone? After register file? Any guess?
Decoder.
No, decoder, the things are already here itself. Let's assume that registers, I am not actually, I assume that the controlling part is done by some circuit. Okay, so that is not part of my abstract view.
Okay, then ALU might be there.
Yes, so then we need arithmetic logic unit. So we need now tell me, so obviously two values, arithmetic logic unit, it takes two values. Okay. Now, other than these two values, which are directly coming from the register file, do you feel that there is some other connection needed at the input other than control signals? I'm talking about data. Think about the arithmetic operations which we have already talked about. We have simple add where two registers are added and one register value and one immediate value.
Yes, ma'am.
So where do you get the immediate value?
From the instruction itself, we get the immediate value.
Right. So it means you will get a value directly from the instruction and it goes here also. So sometimes two values will come, sometimes one value and one direct value will go to the arithmetic logic unit. Okay. Now, after arithmetic logic unit, what will happen? What we will do in the result? Any guess? So the connections after the arithmetic logic unit, that is what we are now deciding.
Where can we read one?
It's not only read, it can be write also.
Sir,
Because we are talking about load and store. So what will be this block? This is instruction memory. What will be this block? Guess.
processor memory interface.
Yeah, this is data memory. It's not processor memory interface. This is and here what you will get? The value which goes to after addition. After addition, what will be this one? This is actually address. And a value directly comes from the register, a value directly comes from the instruction is or not directly comes from the instruction, actually it comes from the register is called data. After the arithmetic logic unit performs, you may require the value to be stored into one of the registers.
Sir, output of ALU should be data, right?
Which one?
Sir, output of ALU should be data, right?
Output of ALU will be data as well as address.
Okay.
Because when it is add R1, R2, R3, these two are added. This becomes data. But when it is load or store, addition value is an address. Got it?
Okay, sir.
So that's why the output of ALU can be address as well as it goes to the data to the register file. When it goes to the data to the register file, when this is the case. When it is load store, then it is address. And when it is load store, when it is acting as an address, you need data. Where from you get the data? In a load and store? Particularly in case of store, where do you get the data? In case of store, you get the data from register.
Registers.
And finally, the output, which is finally the value which is coming from the memory, it goes to the register. And this happens. Why this line is required? Why this line is required? Can someone tell me why this line is required? This line.
Right backing.
Yes, right back. It's not right back, basically. It's not write back. Write back is not this stage. Write back, I have already written it here. Write back, I have already written it here.
Which one is right back there?
You know, add a write back. Write back is this one.
The other is load, last one.
Other is load. This one is load, right? The value comes from memory. It will be written into, this is also acting as write back. Obviously, it's a write back, but this is write back for the load. This is write back for the typical arithmetic operation. Okay.
Sir, can you explain after ALU once again?
After ALU, what happens? The value which comes after ALU can be an address or data. Do you agree with me?
Yes, sir.
When it will be an address? When the instruction is load or store. This
It will
becomes
be
an
address
address.
of what, sir?
It will be?
Address of this memory.
It will be address of the memory location, where from you will do the load operation or where you will do the store operation.
Okay, right.
Okay. If it is load operation, you get the value from here. If it is store operation, you, in addition to that, you also give a value here. That's why this line is there. Is that clear? After ALU, there are two ways. Either you write back the result directly into the register file, typical arithmetic operations, or you use the result as an address to do either load or store. This one is for load and this is for store.
Okay, I got, sir. Got.
And this is for add. Now hopefully things are clear.
Yes, sir.
So this is a conceptual view or abstract view of the CPU. I know that there are many other units needed to complete the job, but you can actually bank on it, and this is a conceptual and abstract view which can at least explain that why the circuit is like this. How we will implement these things, we will see later stage, but at least logically it looks to me correct. Now, if you require some stage, for example, when I was talking about this one, move requires fetch, decode. It doesn't require execute. It doesn't require memory. It requires write back. Only thing is that for move instruction write back, I have not done anything here. For move instruction, it can happen inside the register file automatically. That's why that signal I have not given it. You do not need arithmetic logic unit. You do not need memory. You only need the write back. So that can internally happen. If you look into it, this part, I did not consider anything about the write back for the move instruction. They can automatically internally can do it inside the register file. I do not need to go outside of this. Is that clear? Now you look into this. And
1 minute, please. So last one. Okay.
Let me give you a clear diagram. I shall present it so that you get the view properly.
Sir, output of ALU can be address as well as data, right?
Output of ALU and address and data. Okay. Just a minute. Let me present my screen. I think this diagram will be much more easier. So I'm now switching off my video. I'm now presenting my screen. See this diagram, which I have actually drawn it. Comment on it if you have any doubt. So hopefully now, because it was not earlier visible properly while I was writing, you can see this diagram.
So where you have written address after the operation of ALU, there can be data as well, right? Okay, no, we can directly store two registers, right?
That's why, na. That's why it is going back. It is going back and going to the data port of the register file.
We don't need to store in data memory. Okay.
No, data memory, where are you storing? Why you need to store into the data memory? When are you storing, then data goes directly here, na.
Okay.
You see that there is a data port here. So let me give you, see this part is data port. This is for this is for store operation. And this address is the address. And this part for load operation. This data is for load operation. This data is for store operation. This data is for load operation as well as storing the result into the register file after arithmetic operation. So this data, you are getting it either from memory or some arithmetic result you are getting it. Whereas this data is basically transfer from a register to the memory. Is that clear now?
Yes, sir.
Now all these units, starting from this adder, this instruction memory, data memory, arithmetic logic unit, register file, they are all, and including program counter, they need to be controlled properly. You cannot simply assume that they will be acting by their own. Okay. So that's why control unit part intentionally I skipped. I know that it will not be possible to bring the control unit part here. So here you can understand the transfer happens everywhere. It happens from instruction memory to the register. It happens from instruction memory to this adder. It happens from internally within the registers. It happens from register to the arithmetic unit, from register to the data memory, from arithmetic unit to the register, from data memory to the register, from this adder to the program counter, from this adder to the program counter, from program counter to the memory, from program counter to this adder. There are lots of transfers happening. And these are all parallel lines. Remember, these are all data paths. So all are of 32 bits. All lines are of 32 bits because we are talking about 32-bit RISC architecture. So all lines, they are of 32 bits. Only thing here it is 4 bits, but still this is an adder which adds to binary numbers. If this is 32-bit, you expect that this line will also be 32-bit, but obviously you don't need 32-bit. This is a fixed value 4, so you don't need 32-bit. Okay, so if any doubt up to this, because this conceptual diagram, abstract diagram must be crystal clear in your mind, because our designing will be based on this. Obviously, we will introduce many more components, but this is what we require at least. So if you have any doubt, let me know before I proceed further.
So actually in data memory, the output line, so that is actually loading
Yes.
from the register into the memory.
Output line data memory, that is loading from
Memory to register.
Loading from memory to register. It is loading from memory to register. So logical, all connections which are given logically, you need to understand that why it is needed. There may be some more connection later on, we will see, but at least for the topics that we have discussed so far, these connections are definitely needed.
It's a 60. First one.
Okay, done, good. So I can assume that all of you understand this. Please let me know, because this is simple. If you basically spend 5 minutes of time just looking at the diagram, and if you have followed the discussion, probably you will find that why these connections are there, the logical connectivity.
Mercy.
Done? Okay, good. So now let me go back to the discussion. So we are now left with the understanding that how the transfer happens. Okay. So the transfer happens primarily in a register transfer logic. So we need to understand that how the registers are designed now. Okay. So we will look into the hardware components now, designing the hardware components. This is abstract view. Okay, let me switch on my camera again. This is the abstract view. Okay. Now we will see that how the hardware looks like. For example, how how the register file can be designed, what are the different ways we can actually design the register files. We need to know a bit about it. That is what basically we will look now. So now we'll look into hardware components. So the first one is register file. Now, can someone tell me, based on our requirements that we have already seen, how do you expect the register file to behave? What I mean to say, explore all the instructions and see that how the register files are accessed, whether they are sequentially accessed or you require parallel access.
Parallel access of at least 2 registers is required.
Yes, parallel access of at least 2 registers. Parallel access of at least two registers. So an abstract view again can be something like this. I feel one conceptual diagram can be like this. So there are 32 registers. Let's assume that 32 registers. There are 32 registers inside. So what are the requirements? You give 32 addresses of the register. So 32 registers, that means how many bits needed to uniquely identify a register?
Five.
Yes. So this is 5 bit. This is 5 bit. Why do we require this one address C? Can someone tell me? This is for input port. Register means not only reading always, you also write into the register. So this is input address. So any value which will be written back into the register, you should select the any value which will be written into the register, you require an address. So this is also 5 bit. What about the size of the input data and AB?
Bit.
Yes, these are all 32 bits. Now I want you to mention that what can be a possible difficulties in this design. Someone tell me what can be a possible difficulty with this design. Let me give you a clue that I have 32 registers. They are organized like this. So this is R1, this is R32. Now say this is your output line. Now this, do you think that this is, in abstract view this is fine, I can simply write like this, but do you think that in circuit it is possible like this? What you need to do?
Two output lines we need, right, sir?
No, I mean there is a single output. Let's assume that I want one of the values of these 32 registers to come to the output. What do we require here?
Controlling bit, like which
No.
circuits?
No, that's the control circuit, fine. But what kind of control circuit is needed?
Multiplexer.
Yes, you require a multiplexer. You require a multiplexer. So this, out of this 32 registers, one of them will come. One of them will come. Okay. Now think about this dual port. I need both the values at the same time. If R1 is coming through here, R2 is also coming through here, then I need both the things to be at the same time, then only the addition can happen. So if all the registers are actually connected through the same multiplexer, So you need a port mechanism, dual port mechanism. That means the value again, this is a dirty design I am doing. You can do it in a better way. The same value comes here, another multiplexer is here. So this multiplexer selects one of the values from here. This multiplexer selects one of the values from here. So even if the conceptual diagram looks like this, you can understand that inside the transfer, how you need to arrange it. You need multiplexers to intelligently pass the value from one of the registers to the output channel, and parallelly this one of the values will go to this. This parallelly is a constraint.
So can you repeat what the other line is for, other than output?
This is also output. This is also output.
Okay.
So one multiplexer brings one output, another multiplexer brings another output. Because we always require two outputs. So while you design, basically this is what you are going to do in the lab this week. Designing of a complete register file so that we give two addresses and it produces two outputs parallelly on the two output lines. Design can be done in many ways, whether you use double multiplexer or you use some other mechanism, that is fine. But you can understand the difficulty. You basically, if you want values of two registers to come to this one and this one, the first thing you'll have to do it, this line should be separated. Otherwise it will be serial. One will come, then the bus is free, then the other one will come. Okay. But that will be delayed. So we do not want to delay. We want both the values to be available at the same time. This is for output. Now similarly for input, the address C is the address of the register where it will go. And where it will go, how it will be selected, you require a reverse circuit. So you require demultiplexer.
Address of what, sir?
The third one, the third line for writing into the register. Writing is only with inside one register. You do not write it parallelly to both the registers. Okay, that's why there is only one input line. Input data is only one. Output there are two. For output there are two addresses. For input there is only one address. First of all, you need to understand that why this is needed, why this address C and input data is needed. Can someone tell me that why this address C and input data, these two lines are needed?
The input data is
Where do you want to store and what do you want to store?
Yes.
For that,
so for instruction, so this is required to execute the fifth stage of the instruction. Fifth stage, that is the last stage, write back. Huh? These two lines are required for the write back stage, fifth stage. So address C is the address where you will store and data comes
from the either from the arithmetic logic unit or from the memory. That we have already looked into it earlier. This data is either coming from the arithmetic logic unit output or it is coming from the memory. When it is coming from the memory, when the operation is load. When it is coming from the arithmetic logic unit, when the operation is add, sub, multiplication, whatever may be arithmetic operation. Is that clear?
Yes, sir.
And this one address in which register? Because you are storing into these 32 registers. So you need to select which register. Where are you storing? So that where part, if you look into the instruction like this, add R1, comma R2, comma R3. This R1 is the address of C. Similarly, when you do load R1, comma X R2, this R1 is the value coming from memory. And for this R1, it is coming from the arithmetic logic unit. So this is the reason we require address C and input data. Now, to finally, push the value to R1, you require a circuit. What that circuit is? Because it will come through a command line.
We can again use multiplexer, sir.
Multiplexer or demultiplexer?
Sir, we can like pass the value to like input data to multiplexer and choose the address.
Right. So it depends on how do you implement it. I got it. So you require something, a mechanism which can actually transfer this value from the input port to one of these selected registers. The selection will be definitely based on the addresses. So now you know that if I ask you to design a register file, dual port register file. This is a dual port register file. That means both the registers will be read at the same time. The other way of designing the same circuit can be done. If you look into the book, they actually provide two different ways. One is like this, other can be again the same circuit. Okay, because we need the functions to be implemented. How do you implement it? That is basically the circuit implementation. So you can have a design like this. This is RF1, this is RF2. Sometimes this implementation is also preferred because the handling will be easy. You can also implement like this. Both are copied here. Same register files are copied here. Okay. Address A goes here. Directly you get it. So you do not need a kind of complex output multiplexing. Okay. So you have two memory blocks here. Both are copied here basically. The register files are here, same. So address A goes, the value directly comes. Address B goes here at the same time, the value directly comes. Okay. Basically, we are separating the output ports here. While implementation, you will find that why these two approaches, that I'm leaving it to you to realize that which one is better for you. My objective is I need both the values at the same time and with minimal circuit requirement. Okay. So this is one register organization, register file organization. The other one is I have already shown. So depending on which one you find it comfortable and which one you find it requires least hardware. But my primary objective is I need both the values to be at the same time available to the input of the arithmetic logic unit.
Sir, last one would be less costly, right?
This one you are talking about, na?
Last one.
As a previous one.
Yes, because that needs only there is no need for two separate register files.
Right. There no need to, but you may find some difficulty in implementation there itself. Okay. You require complex circuitry for input-output getting. Okay. So each one has its own advantage and disadvantages. So you can implement it depending on what is your requirement. So, and assume that, now I assume that you have a circuit to do the transfer, okay, from one register to other register that we have probably understood in one of the labs. With that concept, you can actually design the register file for the whole 32-bit system, and that will be used as a library for larger projects, bigger projects. Like essentially, as I told you at the beginning, that our aim is by the end of this subject, all of you must be able to design your own processor, whatever may be the small, but a complete processor with basic minimum functions. You must be, things must be clear in your mind. That is what my objective is. Okay. So hopefully this part is now clear. The register file part. I'm not going into the details of the implementation of the register file. That is, parallel in, parallel out. Register. So what you can do, you can look into the Logisim simulator. You can take the parallel in, parallel out registers as the building blocks and then start designing a complete register file which supports these functions, keeping in mind that you will be using this in your future designs, that what are the options to keep in. Okay, so that is what I want you to explore further. Probably that will be what we will be doing in the next lab also, but this is what we need to do it. So the circuit designing, I am not asking you to design the parallel in, parallel out registers itself, but how the transfer happens, what the additional circuits needed based on my inputs. Okay, so I will be probably giving an input code like this. Say I'll be giving 5 bits value here. This is source 1, this is source 2, or say source 1, source 2 and destination. Okay, so my commands will be something like this. This will be 5-bit, 1 2 3 4 5. This will be 5-bit, 1 2 3 4 5. This will be 5-bit, 1 2 3 4 5. So currently I have 15 bits and I want some specific instructions to be implemented, that is move and we need move, we need load, we need store, we need add. Now add and store, they will be using the same encoding, because in both cases add and load, sorry, add and load. Let me write it even. So move, then add and load, and then store. I need these 3 types of operation. In case of move, so these are 3 operations. I can actually represent it in 2 bits, yy. So when yy equals to 0 0, it will do movement. When yy equals to 0 1 or 1 0, it will be doing add or load. When it is 1 1, it will be doing store. A very simple register file implementation where I need, this is an encoding I am just giving it. Encoding is up to you. How do you encode it? It is up to you. I'm just giving an option like 0 0. This is move. 0 1. This is add. 1 0. It is 1 0. It is load. And 0 1 1 0 1 1, it is store. So my instruction is now 5-bit 5-bit. My instruction is 5-bit 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 2-bit 16-bit instructions. So I want to realize a circuit that will take 17 bits input. These 2 bits will determine that what is the instruction. These next 5 bits will tell that what is the source register. Next 5 bits will tell that what is the source register 2. Next 5 bits will tell what is the destination register. In addition to that, what I will do, I will implement 3 more registers outside this register file. One is for data. Just a minute. Achha, I am in a class actually. My class is going on till 11. Okay. Sure. Okay. So in addition to these internal registers, what I will do, I will implement 3 more registers. These 2 registers will be used for reading. This one will be used for storing the value. I mean to say that you can understand that why I require 3 additional registers outside this register file. This is not a complete implementation of the processor. I am just telling that if I want to implement a register file, okay, how do I check my register file is working properly or not? So I shall be designing the encoding. So my inputs will be 17-bit inputs. Okay. And depending on this, I will decide that what it is doing. Is that clear?
Sir,
Yes.
sir, register file will only like store input, and whenever we want to read that, it will read, right?
Yes, right.
And these, what you were telling is complete implementation, right?
No. See, I am not asking you to do the addition implementation, load implementation, store. But for this move, add, load, and store, the data movement operations are needed, na?
Yes.
So these are all data movement operations. If it is a move, you need to get the value to be transferred from one register to other register. If it is add, you need to get the values from two registers coming outside the register file and being loaded into two outside registers. If it is load, similarly. If it is store, similarly. Is that clear now? So essentially, if I make it a clear design, it should be like this. This is my register file. And here I have I want this. And this will be done through the binary code. This is 2-bit YY 5 5 5. Source 1, source 2, destination 1. This will be given to the system as input. Is that clear now?
And sir, which instructions need to be supported?
That I already told. Na? We need to support the operations for move, operation for add, operation for load, operation for store.
Sir, like if it is move, then what will happen? Like internally,
if it is move, then it will take the value of source 1 and move it to the destination 1. That's it. So it will be internal. Correct?
okay, that should be internally done, right?
That will be done internally. If it is add, it will take the values of S1 and S2, it will put it here and here.
Okay, and after that it will go to ALU if we
No,
implement.
that's what we do not require. ALU require, that's why this is only register transfer only. These are all registers here. RA is a register, RB is a register, RC is a register, external register, and this RF is a complete register file where all 32 registers are there.
So sir, add will only produce output RA and RB, right?
RA and RB.
Okay.
Add will only produce RA and RB. Move will do a transfer inside.
Internally, between
Internal.
registers.
Load will accordingly do it.
Load
And
will in address sheet will load.
Load will Load will not in address C. Load will load it in one of the registers RA.
Okay,
Because
okay,
if you look at the load requires only one of the registers.
okay, okay. And store will store in
Again,
address C.
store will basically store in address C. Okay.
And that will be D1, right?
Yes, that will be D1, not destination. So whatever the value is there will be stored here itself.
Sir, can you give one like examples like syntaxes which will be followed?
Yes, sir. Example.
So if I write like this 0 0 0 0, then 1 0 0 0 0 1 0 0 0 1 x x x x x. If my command is like this, what it will do? It will move. It is basically move. This is register number 16, R16, R17. What it is doing? If I give input like this is don't care. When it is 0 0, basically these fields are don't care. Okay. So what it will do? Depending on the first two bits, it will decide that okay, this is a move. So the value of this one will be moved to this. So if my command is add, it will be 0 1 1 0 0 0 0 1 0 0 0 1 1 0 0 0 2. What it will do? It will simply bring the value RA equals to R1, RB equals to R7 16, R17, and for this one R16 equals to R17. Is that clear now?
Yes, sir.
So accordingly load and store you can do it.
And we can follow our convention, right?
Right, you can follow your own convention. So the convention is there is no actual addition, actual load store happening. It is only movement. Movement is either from here to here or from here to here. That's it. Okay. So you know that these 5 bits will directly go here. These 5 bits will directly go here. These 5 bits will directly go here. And now you design the multiplexer, decoder, demultiplexer, whatever is needed to implement this circuit.
Sir,
Yes.
sir, in load store we require access to memories, but here we will not be doing anything like that.
That's why I told you, no, we do not need it. In case of load, what we require? In case of load, we only require one value to be read here. Okay. In case of store, what we require? The value from this one will go here. That's it. Where it will go? The address will come here. Okay. So that's why this is register transfer designing. This is register transfer. So if I clearly write it, probably in terms of register transfer notation, let me write it. It should be like this: RTN notations. RTN for add will be something like that. What we need? RA equals to RS1, RB equals to RS2. Add is done. Achha, then move is basically RS1 equals to RD. Then we have load. For load, what we need? We need RA equals to RS1. Okay. Then in case of store, we require RD equals to RC.
Sir, RD is any register, right?
RC equal to R.
Yeah, RC equals to basically R. You in case of store is basically you give the value into the RC. Okay, that value comes to the destination register. RC equals to RD, na?
And sir, in move, sir, D is any register like RS2, RS3.
No, that convention you can follow. You know, I have used the first two as the S1 and S2. We have 3 fields. Okay, this is S1, this is S2, this is D. I have assumed that in move it is from here to here. Sorry, here to here, opposite direction.
Sir, move can be between. It is not necessary. Okay. We can use any convention, right?
You can use any convention. You can also do it from here to here, depending on whatever is convenient.
So store should give
Huh?
take from the register file and give outwards, no sir. So it should be
No. Store is
RC,
basically
RD
coming
right
from
into
memory.
RC.
Store is coming from memory. It is coming from memory. So in the design itself, this RC value will come into the register. That's it. That's store. Store is basically coming outside to the register file. Got it?
RC is like a value.
RC will be given as a value, na? RC is an external register. These RA, RB, RC, these are 3 external registers other than these 232 registers. So you will have to implement these 3 registers also.
Sir,
So
my
whenever
confusion,
where is your confusion?
sir, load and store both seem to be taking values and storing into register. Right now there is no way to write into memory from the register.
No, load does not take any value from the register. Load actually loads the value from. Oh, actually, I might have done it wrongly. Sorry, this one will be reversed. You are right.
It looks like the V line.
Store is basically from
But actually both lines
register.
are the same.
Let me write it. You are right. I have done it something wrong. Load is basically from memory to register. Okay. So what will happen in case of load? You will get R. This will be RS equals to RD equals to RC. This is load. Store will be
Page 56 we haven't done.
RA
No. We have to start from page number 56 because we have already 55.
This is for address calculation. This is for data. Okay. What is the format of store? Store R1 X R2. Okay, so you need to read R1 as well as R2. So R1 value, my convention here basically, what I have done, S1 is as used as R2 is assumed to be an S1. This is an address. After adding X, because this X I am not giving here, this is not a full implementation. This is only register transfer. Okay. And since you need to store this value of R1, so also you need to read the value of R1, which is here, and that will go to RA. Is that clear now? These are all register reading operations. Ideally, in case of load, also you require this address. I have skipped it. You can also do that part. You know, you can see that RA equals to RS1. This address is also needed. But actually, why I have not done it here? Because these two are different events. First, this will happen, then this will happen. Okay, but whereas in case of store, both read happens at the same time. That is what I have given these two. In case of load, I actually skipped this part. But you can also implement this. Is that clear now?
From other big animals.
Hello?
Yes, sir.
So what I want that you explore all these options, that how to basically see, don't limit yourself that whatever I am asking to do the transfer. You can also think about your own way, that how to do this. Ultimate, aim is to understand the register transfer happens. Okay. So the best one is realize this. You have a register file with 32 registers and 3 additional registers, RA, RB and RC, and 3 ports, address ports. And now I want to do various types of transfers needed to complete add, load, move and store data transfer. All data transfer related to these instructions. That is what we want to realize. Okay, so that's it. I shall stop today. If you have any query, you can tell me right now.
Sir? Yes. Sir, I have a doubt in the abstract view of the CPU. Sir, shouldn't we send an instruction line to the data memory as well?
Data memory?
Like we should tell.
You are mute.
Like we should tell it from where to load the data also, right? Directly.
No, where to load the data means, are you talking about the instruction data or data for calculation?
Data for calculation, so data for calculation.
The address is already given going now from arithmetic logic unit. From arithmetic logic unit, the address.
Butterfly.
Look into this. This is the address, no? This is the address. So this address is nothing but x plus R2. This is x plus R2. And here the data goes R1. So if the instruction is store R1 comma x bracket R2. So x bracket R2 comes from here, R1 comes from here, and the store operation happens. If it is load R1 comma x R2, then x plus R2 comes from here, and the value comes here and goes to R2, R1. Okay, is that clear?
Yes, sir.
Okay. Good. So if there is no more question, we can stop here, and Friday morning again we shall continue our discussion. Okay, then thank you.
Thank you.